So first topics that we're covering in linear algebra is finite vector spaces. And you're probably familiar with this way of writing a vector. And with this way of writing a vector. And quantum mechanics, due to Dirac, write vectors in the bra and cat formalism, and you can immediately see if someone is a mathematician or a physicist according to which notation one chooses. Okay, what does it mean? We have a set of n numbers, that's why it's finite. And their position, they're ordered, the position of these numbers is important. How do we call the number of such components of the vector?
Quantum?
Something that you're very familiar in daily life. When you're writing down a point in real space, how many numbers do you use?
Oh, dimensions?
Dimension. 3.
Oh.
X, Y, Z. That's how we write our good old beloved notation of vectors, and it's dimension 3. For finite, we have some finite number, not necessarily 3. It is anything. Typical dimensions of a quantum system is much, much larger than n. Well, actually, you have met already a vector that has an infinite dimension. Psi. Once you have an infinite number of components, that's a function. Right? Because you have a real number instead of a natural number ordering the results, the entries in the vector. Okay. The only other thing that is a bit different in these vectors than what you're used for in vectors for mechanics, for example, is that UI are complex numbers. Okay, in real space, we don't usually use complex numbers to set positions. Okay. So what can we do with these vectors? We can add them. Known as, in the lingo of linear algebra, as linear combination. So if I have a vector u plus a vector v, I write it down. More traditional can I add any two dimensions? Any two vectors?
Yeah.
No. It's not,
Oh, they have
the same dimension.
They have to have
It's
the
the
same.
same dimensions.
Multiplication. I multiply u, vector u, by a scalar c, which can be, of course, also a complex number. Every place that I say a scalar, it could be a complex scalar. What other form of vector multiplications do you recognize? Do you know?
Dot product with cross product.
Yeah, dot product or cross product. Scalar, not multiplication by a scalar, but scalar multiplication that sometimes is known as a dot product. We multiply two vectors and get a scalar as a result. Okay, so that's how the notation. Oh, we have here a new a kit. What does it mean? In our usual way of writing it, first of all, it's not a row. It's not a column, it's a row. Second, and extremely important, it's complex conjugate. So let's try to understand what this means. I'll go back to this usual notation. Just a moment. So all these are equivalent definitions of the multiplication. This is times same index that appears twice. So we'll use all of them whenever if I remember correctly, this is okay, so let's take this notation to explain all two functions. When I'm going from a summation in discrete space to summation in continuum, what's it called?
Integral.
Integral. Okay. So integral. On what do I do the integration?
On the dot product.
No, what's the variable? X.
It's on.
X now represents I. And U and V are two functions. So this forms that you are starting to recognize from our calculation of averages is just a dot product or a scalar multiplication. Okay, we have also cross product, not relevant for quantum mechanics. We won't have any use for it, so fortunately we won't have to go this way, like electromagnetism, to determine the direction of the vector. But we have one other multiplication.
Operate on the vector.
No. We haven't introduced operators or matrices like this one. There's another multiplication between two vectors. Outer product of two vectors. Any one of you have run into it? Okay, so this refresher is useful for something. So an outer product two vectors.
Convolution.
No, you don't need your hand for it, because it doesn't give you a vector, it gives you a matrix. How's that? Okay, this multiplication we know. We take the first one. This guy is the same idea,
1 times the whole.
just in the opposite of order. So how do we do that multiplication? The same law as here. We take the first in the row and multiply it by the first in the column, second by the second. But here I have only the first number in the column and only one number in the, first column, first number in the row and first number in the column. I don't have anyone else, right? So
this is the same to multiply between polynomial and another polynomial?
yes. So
And
I
like
get an n by n matrix.
Like you multiply a sum with a sum with another sum.
No, here I'm going a sum around the row. But here, if I write it the other way around, I have only one in this row, right? Here I should have sum on the column, but the column is 1. Yes, but here I have all. So what happens with all the other cases? The same, but they're written down as a matrix. And this has a neat representation. Okay, because this actually says sorry, I've misplaced the complex conjugates. Because this is the complex conjugate. It's nice with the notation, this notation immediately tells you which one is complex conjugate. Okay, so that's outer multiplication. It's very, very useful when you're doing many particle quantum mechanics, which we are not doing in this course, but it has also some usage that we'll see further on. What other kinds of multiplication we can do? That's basically what we need at the moment. Some general rules about all these multiplications. use the definition. Okay, so what do I do? Step by step, multiply the vector v by the scalar a, multiply the vector w by the scalar b, add them, and then multiply them. You can prove to yourself immediately. Just use the definitions. There's a simple reason. This is known as the norm. Just notation. Now, from our previous knowledge about quantum mechanics, what do we know about this norm? Could you repeat, please?
It's supposed to be 1.
Right, the norm of a vector in quantum mechanics must be 1. That's probability. And now you have also learned how to normalize a vector, something that everyone who's doing quantum mechanics is doing all the time. This is a normalized vector. Pay attention, this guy is the square root of the dot product of the vector.
the last?
W?
No, like the V shape, like.
A scalar A times vector V, scalar B times vector W. I
So
write it
What's U?
so here.
It's a vector also.
Oh, everything that appears in a brow or a cat is a vector.
So what do you need to after I after the
Well, that's just to remind us that the result of this summation is a vector. You could have just simply written out instead of
okay.
but it just helps us to remember that the result is a vector. It's if you want mine to write it the other way around. Where it comes useful, let's give you a teaser or question. What would be the result of U equals V? Volunteers step up,
It's not the same.
come to the black book. So try, come. We won't shoot anyone for a wrong result.
I
That's all one can request someone in life.
So this one is a vector. This one as well. So this one. But I'm guessing that this is scalar and this is scalar. So this is probably like this. No?
Same thing.
So does it better if like one or the other is complex?
It's always important.
Oh. Okay, so I got confused.
Okay, so
I guess that.
okay, why this is not the answer? Because this is equivalent to this guy, but according to one, this is the opposite of this, right? So it had to be your complex conjugate. So actually, this must be the answer. And now, how can I glean it directly from here? That's why I'm using this outwards to remind me. Okay, I have to rewrite this guy, right? So if it's on the left, this is the first guy. This is the second guy. And both of them are multiplied by u. Yeah, so it's and now using rule 1, it's That's exactly what's written. So, complex conjugate is something that should come naturally to you in all stages.
Yeah.
You've learned complex.
No, but you said that like no, the function itself. Like thinking about what you said to us last lecture about that the square function can be negative. It's like so.
This could be a complex number. Scalar multiplication can be a complex number. I didn't say that a scalar multiplication has a physical meaning. Okay? Orthogonality. What do you remember from the usual way we vectors? Let's say orthogonal set of bases. Not more than zero. Two vectors are orthogonal if their dot product, scalar product is zero. Let's say I have a set of vectors. An orthogonal set would be a set that for each pair that I will choose there, I multiply two vectors. If they are the same, I get some result, and if they are not, I get zero. So it becomes orthonormal. The multiplication of two identical vectors always gives me 1. And I hope all of you recognize chronic case that it's 1 if I is in the orthonormal, we could also define an orthogonal basis. Orthonormal basis. Where n is the dimension of those things. Can I have an orthonormal base with n plus 1 vectors? No, you can't. Can do it. I won't spend time on it. So if I have a size, space of size n, dimension n, I need n bases. We're writing some dimension x, y, or r, etc. Never have 4 or 2. So what does it mean? Explains that if you have a vector u and I have a basis e or epsilon, I always can write it as a linear combination. Excuse me, but how do I build these constants AI? So we know to do it already. Sure.
Maybe if you do a dot product of u, for example, with epsilon I, that would give you a thin AI.
Exactly. Let's take this guy and multiply it by some epsilon.
Oh, you get the good.
I just use the definitions of multiplication, vector multiplication that we have already studied. Epsilon is an orthonormal basis. So this guy
vector u is a sum of a number
Times,
multiplied in a set of vectors.
right. And now if you haven't thought about it, I'll blow your mind. Basically, it tells me, are there any special basis for a space of size n? How many bases like this do I have?
Infinity.
An infinite number of such bases. Now, side remark, you'll see that in quantum mechanics, some of them are better than others. But at the moment, for mathematics, all of them are equivalent. So, let's stop a minute and look on a 2 by 2, a dimension 2 space. Okay, so if I'm writing a vector 2, 3, what does that really mean?
That there is a set of vectors that you can add.
Actually, what it means is, in the regular representation, it means
2 times 1
plus 3 times 1,
0 more 1.
0, 1. Thanks. Okay? I don't like that. Why? For no reason. I much prefer the bases instead of 1, 0 and 0, 1. I like the bases why? First of all, is this a basis? Orthonormality. Let's check. 1 times, well, I didn't write any complex numbers here, so don't have to worry about it. Let's check of orthonormality, right? One times 1, 1. 1 times minus 1, 0. 1 minus 1,
Oh, yeah, yeah.
sum 0. So I have half of these two. The first one I get 0. 0, 0, orthonormal. Okay? So it's a basis kosher as any other basis that they could have chosen.
To check, I mean, it is orthonormal, but to check orthonormality, don't we need to dot product one vector with itself? Because if it's 0,
Right.
it would be, of course,
That's a 1 over square root 2.
Yeah.
You are right. Something I can do and you can't. Okay, now I'm checking that the orthogonality I checked. Orthonormality, okay. Square root of 1 over square root of 2 squared. 1 times 1, 1. Write it now. Plus 1 times 1, 1.
yeah. Sorry for being annoying.
No, you're completely correct. 2. 2 divided by 2 is 1. can do it also for this guy. Won't change anything. Still right. Okay. Yes. You raised your hand. Okay, so I want to write my vector in this spaces. Okay, how do I do it? Okay, what do I want to write actually? I want to write the vector 2, 3 as I called A. Okay, so stay with the notation. A1 the square root of 2 of 1, 1 plus A2 square root of 2, 1 minus 1. Yes? That's actually what's written here. How do I do it? I can either write down a set of linear equations or use what's written here. Okay, so okay, so the answer is does it work? 5 halves minus half is 2. 5 halves times minus 1 times minus half is 3. Okay, so this is a bit of algebra. I think that this form is easier than to solve the linear equations, but it's still, at the end of the day, the same. Now I can come and say, you know what, this notation is too hard for me. I have to write this whole thing. I can say that if this is the base, the way to write the this is the way to write the vector in the space. Why? Because I will just write down A1 and A2 as a vector. So what is the meaning of this notation that we thought is basically the notation of writing down a vector? Please.
So what's happened? How this vector became this vector?
Because what does that mean?
So this is the A.
Right, this is equivalent to say V over 2 of E1 minus half of E2. So what am I writing here? Just the scalars that comes before the basis vector. So what is the meaning of this notation? That's the meaning of the notation is simply under the convention that you are writing down your basis always as and so on and so forth. So you're just so under such a basis, you're just writing that's the meaning of the notation. But if I choose, if I tell you this is my basis and I'm working with this base, fine, so write it down the other way. Choose another base, write it down. Another. So, one thing that we'll need, since we agreed that there's nothing holy about a certain basis, the way to transform a vector from representation in one base to representation in another base. Someone can guess how it will look?
Same vector. I forgot the name.
How do I transform a vector to a vector?
Oh, a matrix.
It'll be a matrix. And since the norm has to be the same, it's a Unitarian. We'll define everything that's just a bit. Okay, till here, people who you have met, you know, something was new or outer multiplication. Everything else we've seen something or other, and perhaps a bit of notation. Okay, so we're moving to operators. So an operator omega, in order to emphasize that it's not a scalar, but an operator, we'll put a hat over it. Takes a vector, returns a vector. If it's a linear operator, and since one is a linear to all operators, what can be said linear operators. So if I use the operator on the vector A times U, where A is a scalar, I get A times B. So I rewrite operator U in some basis. So what does that mean? It means that if I know how the operator transforms each one of the basis vectors, I know how it transforms any vector in this space. Because it's just a linear combination of the transformation of each basis. Someone can guess why do I need this trivial definition?
For example, if you want to use A times a scalar times U, that would be scalar times the matrix, the identity operator times U. And then you could use it, for example, a more difficult and complex equations.
I wanted something perhaps simpler, but in a different direction. Why do I need an identity? Usually in mathematics, I need an identity in order to define an inverse. So, and I'll use it shortly. Now let's say I have two operators. Well, let's assume that I don't want even to write it as a matrix, just definition. So it would be first apply B on U, you'll get
Sensitivity.
or the lack of.
Oh.
You'll get some vector V, and you'll use A on V. Okay? Not necessarily. It could be equal, but it's not necessarily equal. How do I know it? Well, I can give a simple example. Rotation. 2 dimensions, 2 rotations are always associative. Let's say go quarter of a pi right, and then go, let's say, half a pi right, and then another pi right. So I do half a pi, and I end up here. Okay? I do it the other order, half a pi, and then a quarter. Many different examples. Well, even a better and easier example. If we'll write it down, now let's write it down as a matrix. The matrix we know already when matrix multiplication that it's not equal to matrix A times matrix B times a vector. This has extremely important consequences in quantum mechanics. Okay, so we defined I. As I said, we want to define an inverse of an equation. So I operate with omega on D, operate with the inverse of this operator, and I'm back to the same vector. meaning that if I have matrices, if I multiply those matrices each other, sometimes instead of writing down epsilon sub k, I just write k short. So basically what I'm saying is the first basis vector is the secondary. Has been done. Okay, what else do I know? I should know something about what omega does the basis vectors. What can it do? What does any operator do on any vector? Transforms it to a different vector. Okay. So I'll get here some vector, which I always can write as a combination of the n vector bases that I had. Times some scalar, that's any vector in the space, and I have to write to myself an additional index to remind me that that's what is happening to the kth basis.
What did you get?
B is just some scalar. The logic is this is some new vector. What is a new vector? Some combination B times the basis. I have
Why do you have the K?
because if I take a different K, I will get a different set of B's, right?
Yeah. Okay.
Similar to the way that we teased out the value of the scalars representing any vector. I'll multiply it by k prime, let's say. Step. Right? Just copy the definition of omega times k. This is our beloved delta function.
How did you do the last step?
K
No,
time
no, from up to
from here to here.
yes.
These are scalars, numbers.
Yeah, I know. But how did you take the K tag inside?
Because it's a linear combination. It's a linear operator. I'm always allowed to take the scalars before.
K prime is a basis vector, right?
Yeah. Equal or different than k. Okay, so what I garnered from here, what did I learn from here?
That k and k tag are orthogonal.
So if you
No, that I knew by construction.
if you use the operator on a basis vector, you always get to scale. That's what you mean.
No, because I don't. I get a vector, an operator on.
Oh, I forgot. Yeah, I forgot you jumped.
No, don't get confused. Still, the basic definition that an operator operating on a vector gives you a vector remains correct. Correct.
What was the question again?
What did I learn from this?
Basis.
No, that I knew. I used it.
Yeah.
If I didn't define it, I wouldn't get it.
And you can get the scalars by doing this.
Basically, I got all the elements of the matrix. I know now how to calculate the elements of the matrix. Because
That goes for every L and every. That's why you use double instead. Okay.
remember, we started with trying to figure out this guy. Okay? Just to be consistent, we'll change the That's exactly what it taught us. That you want to write the matrix of the operator, take this scalar multiplication with the operator within for each possible combination of basis vectors, and you'll get exactly what it does for the transformation of the vector written in this basis. So if you have an operator and you want to write it down as a matrix, just choose your basis, perform this calculation of the the operator does. Okay, you see the taste.
If you have a matrix, can we turn it first?
A matrix is an operator, but it has to go through some kind of conditions. But it tells you how to build it. So,
Now, how can I know how to do it without knowing what it is?
you have an operator. If you know what the operator does to a vector, I'll give you an example that you already know. What did you do there? Right? This is exactly the matrix element of the momentum operator. And the average of this operator are the guys along the diagonal of the
All the averages?
the average for the first basis function, the second basis function. So you could just sum up. You know how your vector is built? Because what do you do here?
Then I know how to make it a matrix.
Take all the bases, perform whatever this operator does. You know how to write them.
So this is actually the expected value of, I don't know.
So this is the expectation value for the first basis vector, for the second, for the third. What are these mixed? We'll see.
But if I have like a vector that have finite numbers of spaces, but it has infinite but only finite.
Right, so
So the rest is zero.
the rest will be zero. Life's good. Let's calculate. Let's meet an example of an operator which at first sight will look extremely bizarre. It turns out to be very useful. Projection. Well, it's an operator, right? It's an outer multiplication of two vectors, and that's a matrix, and a matrix is an operator. What does it do? Okay, in order to learn what an operator, what is its utility, what operation does it perform, we'll use it on a vector, on a general vector. So P of k that works on some vector U. Use the delta function. Throws out all components except the components are along the k basis vector. Let's say if I had in three-dimensional some vector, some x times x hat plus y times y hat plus z times z hat, and I'm doing the projection in the x direction, I'll get just a component in the x direction. Equivalent.
But you have to have two bases.
No, I have here only one basis. It's on the same base. If it wasn't the same base, they are not. This doesn't is not fulfilled.
So what does it exactly do? It takes all the components except
this had at the beginning n components, and I ended up with one component, only along the k direction, the direction of the k vector. What is disturbing you?
I'm thinking.
Someone can tell me what is this operator? Identity, exactly. Because if I go and sum up all the components in all different basis vectors in all directions, I reconstruct the original vector, meaning it does nothing. This is actually a very useful trick. Let's just prove it. Okay. Let's write it down explicitly. all the scalars, right? Good old friends, the delta function, that's why we are working all the time in orthonormal basis, because it gives us just a delta. Which is the same. Okay. Again, I'm using some operator omega on a vector v. Okay. I'm allowed to do this. A number times the or I can't change the order. Now a number times the value. Okay, let's do an intermediate step here. Okay, so I'm rewriting it as sigma L U L K omega. You can move it before I don't care where it appears, before the summation, after the summation, in L.
Yeah.
That's what's written.
Okay. Yeah.
Okay, this route didn't help me much because here I just got the root of L. because all I did is take out this scalar,
Okay.
move it before the operator because it's a number. Number times an operator is equal to an operator times a number. That's it. The only point is that here, if I don't exchange the u and omega, I get a trivial answer that I knew before. And here, when I change it, I get a new way to look on it, which is
Why that the second way is more intuitive?
this we actually have seen. This is just writing u as uk times k and moving on. Okay, but one can't argue about one's.
So what the conclusion
It behaves as a matrix even if we insist on writing it in the Bryan-Ket representation. The only thing that we need in the Bryan-Ket representation is a summation on the projection, which immediately gives you the matrix. Okay, so the remaining 15 minutes I'll give you all of this for infinite vectors, meaning functions. Just an infinite vector. This indexes are and t. But actually, well, let's leave here. What do you understand immediately? The fact that we're working here with R is because we chose some kind of basis that R is the index. We don't have to necessarily work with R.
So it's like coordinate system.
No, not a coordinate system is trivial. I can't decide that I want to work with a basis of P at the moment.
Oh.
Another set of, I didn't define what are the basis function of the R space. And the reason is that it's a bit sick. But
R is an index, is not.
R is an index. In position R in space, you have this value of the vector. You want more? But in position R and T of space-time, you have this value. You go to some other, you'll have a different value. It's a continuum because R is a continuum.
So you sum on R. Yeah.
I actually want to remove T because when I'm writing it in this way, I don't even care in what basis you work. Give me a basis and I will know to transform it. It's more general. Adding two vectors is adding two functions. What else do we need? Scalar form. Matrix. So you can see if we know how to write it in a basis for which omega is easy to perform, life becomes much simpler. Okay, operators. They deal exactly. Okay, suppose that just comment. Hilbert space. What is that space? It's a vector space at the space. I need to operators. Remembering that the definition now is this is an action and okay, let's finally define two operators and show that they are not let's choose two of them. Operator is X and operator is let's see what is x times px. Okay, for any value that I would like to calculate, let's say average or whatever, I have to do can't just change arbitrarily the order of a function of R and some derivative of R replacement. So, operation operators also in terms of space. Okay, so basically, except for introducing one additional property, well, two things. We'll introduce what is a Hermitian operator then we will see how all this matter is granted